So thank you for the invitation, and thanks for the kind introduction. It's always a pleasure to talk at IIT Madras. The challenge is for me to figure out how to position the talk differently every time when I come to IIT, because it seems like an annual event coming here and talking, because it's really my favorite venue. I'm going to talk about AI in the loop for healthcare. I used to call it human in the loop system, but now it's the other way, because with the advent of all these models and stuff, AI is there everywhere in real systems. So I'm trying to view this whole thing as maybe AI is in the loop in every system that we use, and specifically in the context of healthcare. A big caveat, for the broad interests of the audience, I've really placed the talk at a fairly high level. So if you want details, we can meet after the talk. I'll be happy to explain. More recent details, Saurabh is also with me. He's a grad student from UT Dallas, who's got his hands more dirty on the data, so we can still talk about it as well. So thanks to everyone, and particularly I'm going to highlight Saurabh, Atresh in this talk, because they have been working closely on the medical data. I'm very proud to say that we have a retired pediatric surgeon, Dr. Mike Skinner, who's probably as old as my mom right now, and he is a PhD student in the lab, and his expertise with everything is amazing, and you can see how his thirst for knowledge is kind of driving all of us as well. So, and then we have many PhD students who have passed out of our group, and particularly I want to call out Nandini, Devendra, Shuo Yang, Tushar, because they have worked on many of the data sets that I'm going to talk about. Of course, thanks to all our collaborators, particularly the clinical collaborators, who are a lot to list here, and the funding agencies that have continuously funded us for the last few years. So with that, I want to talk about this is who we are and what we do. So the way I think about it is, this is our group. We call ourselves the Starling group, the Statistical Relational Learning group. And the way I think about it is, we are inspired by problems from the outer set of hexagons to develop fundamental solutions in the inner set of pseudo hexagons. So for instance, we look at financial, back in the day we were looking at financial NLP and information extraction, and we were developing some statistical relational learning methods. Now we look at many problems, including postpartum depression, side effects of drugs, and I'll give you three more healthcare problems, and then we are learning graphical models on top of them. So we develop learning methods for graphical models, constraint based methods for score and search in graphical models. So that's what we do. And as was mentioned in the bio briefly, we do human in the loop learning. We work with structured data, machine learning, RL, and graphical models. So that's what we do. So when actually I always say that one of the parting advice that Dr. Dietrich gave me was, Sriraam, when you're leaving here at Oregon State, I was a grad student, and he told me this very clearly, and I still remember it, which is that he said, you should have a 5-year plan for the tenure process. You have to think about what is the next big problem that I'm going to solve. But then you should have a 10-year plan that will take you to the next step, and then maybe like a career plan, which you will probably not finish and somebody else will take over. So I've been very keen on thinking in that terms. So I have a small myopic view, and then a reasonable longer term view, and the ultimate view. And the longest term view for me is to develop human allied AI, where we build systems that can seamlessly interact with, learn from, collaborate with. And I used to stop here, but recently we have made some new findings that can potentially teach back the human expert. So I'll give you a couple of examples as we go through, where we found these interesting associations, interesting things that popped up when we were learning these models on real data, that we are able to teach the human back some of these findings. And I'll talk about one of them as we go, right? So what is this human allied AI? And then as I said, I'm now thinking of it as AI in the loop. So I always imagine this kind of a situation, and I'll give you this classic example. If you have heard this from me over the past few years, I'm sorry, you have to sit with me for this one. It was in 2014, we were in the doctor's office. I twisted my knee, and we were in the doctor's office. The doctor was asking me all kinds of questions, and I was an assistant professor, so I was pretending to be busy. So I was just looking at my phone, and I gave him all the answers, and then he asked me this final question: have you told me everything? I said yes, and that's when my wife nicely gave me a whack, and then said, you have diabetes, and you didn't tell him. And the doctor was like shocked to hear this, because it was an urgent care, we didn't have an integrated system, and the doctor was shocked to hear this because he was going to give me steroids, right? And so imagine an assistant sitting inside the system which could prompt the doctor and say, hey, Sriraam has diabetes, right? Of course, it's not a taboo, I'm telling you, so I would gladly tell the doctor, right? So you could easily say Sriraam has diabetes, so maybe you shouldn't prescribe the steroids. And the doctor would say, no, he's in acute pain and his diabetes is under control from what I see. So I'm going to give him this short-term steroid course. I'll increase his metformin or whatever, even a short-term insulin to bring his blood sugar down, but he needs the steroids. Or the doctor could say, thank you for letting me know, he didn't tell me, so we'll change the course. So depends on how the doctor wants to proceed. And you know, all of us have been to several doctors and you can see each of them has a slightly different personal style of how they do it. They don't agree, not necessarily on the treatment every time, but even on the diagnosis every time. There is a small differences because you know that's medicine. So what we want is kind of like a personalized system where the AI system sits inside and we think of it as a Starling agent. It observes what the doctor is doing, it observes the electronic health record of the person that it's looking at. Then it should understand why the doctor is taking these actions, maybe update its knowledge base, present its knowledge to the doctor, and then finally approve, or not quite approve, but accept or suggest alternative treatments. And we want this to be a continuous learning framework. And again, I'm at this point I'm agnostic of the underlying learning method. I'm just saying that it would be great to have a learning system like this. So what I'm going to do, hopefully in this talk, is I'm going to focus on 3 healthcare problems that I think are extremely interesting, and I'm going to motivate our methods through these healthcare problems. I'll tell you that I'm not going to talk about several others, and I apologize to my grad students who worked on things like Alzheimer's disease predictions, survey based predictions. We also had cardiovascular health on children. So I'm not going to talk about those projects. I'm going to instead focus on side effect of cancer treatments. So we had a whole bunch of research projects in the last 10 years that I'm not going to talk about. I'm going to present 3 specific problems. The first one is actually a problem that I've been working for 13 years now. When I joined in Wake Forest in 2010, my then boss, Dr. Jeff Carr, who is now the head of the bioinformatics at Vanderbilt University, walked in and he said, Sriraam, I have a gold mine for you, right? And this was my first week at Wake Forest, so I thought, you know, we are in our honeymoon period, so it's just going to be nice and all that stuff. He spoke to me for 45 minutes and we walked out. I said, Jeff, you have no idea, this is not a gold mine, this is a diamond mine, it's a platinum mine, it's a vibranium mine, it's one of those things that we could really work with. Here is why. This is a clinical study that started in the US across 6 centers led by Alabama in 1985. Okay, so they brought 5,000 people who were between the ages of 18 and 30 in 1985. Okay, and they measured a whole bunch of things. Of course, they didn't have all the technologies back then, so they couldn't measure everything, but they started measuring a whole bunch of things. Okay, and then they were brought back in 1987, 90, 92, and then it jumped into every 5 years, right? So 95, 2000, 2005, 10, now we have 15 and 20. So they've been bringing all these people, and now, I mean, the questions pop out automatically, right? Can we look at the data from 1985 and predict who's going to have a heart attack in 2020? And it's so cool. Turns out you can with a reasonable approximation, right? And I'll give you some findings in this problem. And again, we have multiple data sets. I'm going to focus on this Cardia data that I just explained, okay, on this task. The second one, and this is where Saurabh is currently funded on, we have a recent NIH grant on adverse pregnancy outcomes, where we are looking at a population from Indiana. We have a bunch of nulliparous women. This is women who are pregnant for the first time, and we are trying to avoid many APOs, adverse pregnancy outcomes, things like preterm birth, preeclampsia, gestational diabetes. Is there anything else that I forget for the new moms to be? Hypertension, yes, hypertension, new hypertension. And so we are trying to, I mean, our long-term goal is to reduce preterm birth, because for a developed nation, US has very high percentage of preterm birth, and actually multiple complex births that are happening in the United States as we are speaking. Turns out in India, we have 17% of preterm birth, and that's a lot. 1 in 5 kids nearly are preterm, and so we want to see how we can avoid it. I mean, there are certain things you cannot avoid, like age, right? You can't tell a person, go get pregnant when you're 17. That's not correct. So that's not what we are going to do, right? But we can we find some other interventions? Maybe detect gestational diabetes early enough that we can reduce the chances of preterm birth, avoid preeclampsia, so that we don't need to force the women to have a C-section right then and there, right? So we can do things like that, and we are trying to see how we can avoid this. This is also, we are collaborating with Professor Himanshu Singh here on the Indian cohort, Garbini, and we will talk about the two different cohorts as well. The last one that I want to talk about is, this has been something that I've been doing for 15 years on looking at electronic health records. Easily one of the most messiest data that you can work with, okay, because I can tell you that they're changing the coding every now and then, but even the electronic health records has multiple entries for a single person. So in Wake Forest, when I was working, we were looking at predicting, what were we predicting? Predicting readmissions. How early would somebody be readmitted? And during discharge. So when you're discharging this patient, can we figure out, when we should get the bed ready? Because many people, and this might be a joke, but it's really true. Many people apparently, when they have the heart bypass surgery, the first thing they do is go to McDonald's, and that's a very well established thing. So we were trying to predict who will be readmitted, and in that case, there was one entry for this person where the doctor had suggested some medicine. The nurse had given a different dosage, presumably because she saw a reaction of some sort, but for some reason had written a slightly different dosage on the bedside. And the third one, the last one was, the pharmacy had built a completely different class of medicines because the insurance will not pay for what was paid for, what was given to the patient. So we had this thing in just one entry, and we have, which one should we use, right? So there's a lot of noise, lot of interesting lessons that we have learned. So what I'm going to do is try and motivate all this from the perspective of human allied AI, okay? And then there is a lot of challenges when you work with these types of learning models. As I said, different types and formats of data, multimodal learning is extremely important. Although, most of my talk, it's going to be single modal learning, but multimodal learning is key for all these. Different scales of data. Many of you are young, you have probably never visited a hospital for yourself, that is. I go to the hospital 4 times a year, and so, we have different data points for each of us. So standard things like hidden Markov models and dynamic Bayesian networks don't work that easily on this type of data. Again, different frequencies of data streams, noise, I just talked about something. The most important one is changes in acquired knowledge. I mean, particularly in clinical medicine, the knowledge keeps evolving over time, and you don't want to be, very rigid in your adaptation of these knowledge, and you want to be able to refine your model based on the new discovery that's been made, right? I mean, come on, when COVID started, I don't know how much you guys did, we had to wash our vegetables with turmeric and whole bunch of things. We had a big procedure to get the vegetables from outside to inside the house, and it's Texas, so if you leave it out for half an hour, that's it, the vegetable is gone. So it was very high pressure, and then now that wear masks, so you understand how the knowledge changed over time. How can our models change, right? And then these are really hard ones, right? Partial observability, long-term effects, we don't even know. So I'm going to skip these, but hopefully we will handle some of the top ones. But the biggest challenge, in my opinion, when I'm working with all the clinicians and of course students, is this, right? Because everybody wants to do deep learning, and I have to tell people, no, you don't, no. Cool down, it doesn't work, because there is this, again, one of my good friends who is a doctor comes with 8 features, 200 data points, and wants to run deep learning on this, right? And so you got to explain, tell people, you don't really do this. It's okay to have a shallow model and still learn a good, classifier. I have been lucky with students, but I have also had students come and tell me, if you're working in deep learning, I'll work with you, otherwise I'm not. Right? We can work in deep learning if we do medical imaging, that's great. But for the data that I'm going to talk about here, there is not going to be any deep learning, okay? I expected about 5 people to walk out, but that didn't happen, thank you. Because it happened the last time when I said this, so that's good to hear. So in my opinion, there are 3 steps to human allied AI, and I think of the foundational step as the most important one. You need to be learning mainly from data. You need a model that is efficient, effective. So you have good performance and it can be learning with as smaller data as possible, but still you need it to be generalizable. At the same time, it needs to be personalized. So we need both, right? And there are models that are capable of doing that. And then of course if they are explainable, then it's great because you want it to be interactive with the domain expert. The second step is where you can bring richer forms of inputs, that is not just the data. So domain knowledge, again in clinical medicine we have decades of knowledge in some problem, in some we have a few years of knowledge, and in but if you think of astronomy and other things, we have centuries of knowledge. So we have knowledge in many fields that exist for a long time. And I said, when I introduced Dr. Dietrich, I said that he is one of the founders of machine learning, and because machine learning has been existing in the current form for about 40 years. It's again, many people think it started from 2014, it did not. It's been there for a long time and people have been working on it. So we have a lot of knowledge in many fields and we need to be able to incorporate this knowledge. But there is a key final step in the ladder, which is making a system know what it knows and solicit information about what it does not know. So in some sense, this is inspired, for me, it's from the kids, right? My kid is now 8 years old. We used to build Legos when he was 3 years old. Around 5-year-old time, when it was peak COVID, he suddenly one day said, "Dad, shh, I will do this. I will ask you a question if I have it. Till then you keep quiet," right? And that was my aha moment, because it tells me that he knows what he knows and he knows what he does not know and he knows when to ask that right question. Can we make the systems do the same thing? Can it ask the correct question when it somehow models uncertainty? Again, not an easy problem. We are making some steps in these directions. So these are the 3 steps, and I'm going to motivate each of these steps based on some of the studies that we have. Professor David Page kind of talked about this in the invited talk at COTS last week, and this is really what got me into this whole field, right? And when we were working with Professor David Page, there are these bunch of medicines in the US called as COX-2 inhibitors that were very famous in the late 90s. So in 1998 to 1999, there were these medicines called Celebrex and Vioxx. These are for muscle injuries and tears. They prescribe this as sort of a painkiller to smoothen the pain, right? And even for dental surgery, this was given back in the day. And then in 2001, I think if I'm correct, if I'm quoting it correctly, they were second only to Tylenol, which is the US version of paracetamol, that is in terms of the sales. And then in 2002, people started looking at these with a lens, because there was a lot of reported side effects. And in 2004, they pulled it voluntarily from market. And then in 2005, they had to remove one drug from the market because the company did not voluntarily pull it out. So what is the side effect? Heart attacks. They were looking at heart attack. These were causing heart attacks, and so they were trying to figure out if this has to be pulled out. So we looked at the data between 1999 and 2002. This was back in 2008. We were looking at the data from one hospital called Marshfield Clinic in Upper Wisconsin, and we ran a simple learning algorithm. I mean, it's a AAAI paper where it was essentially learning in reverse. But what we got was that if you ran this, we looked at the first 10 reasons of why this, 10 predictors of whether somebody is on this drug. And if you look at all these, the other ones that are not in shaded, these are muscle injuries, orthopedic aftercare, then chest trunk, chest wall, and then oral surgeries, and aftercare following surgery of a nervous system. So these were the reasons why the medicine was given. But you look right here at number 9, heart attack popped out. So among the top 10 reasons, these were the reasons why the medicine was given, but among them heart attack was a key reason. But the most interesting one was, to me, the first one, which is that it was an elevated glucose level. So there was always, and when we presented this to the doctor, he was going, aha, you know why? Because many people actually thought that heart attack was caused by an abnormal glucose level. Of course, they couldn't start a new clinical trial, right? We don't want to kill more people in order to establish this truth. But the fact that there is a connection kind of made this very interesting. And of course, we had a bunch of grants following this and worked on this. So David Page has done a lot of work in this direction. So I'm going to jump into my topics, and hopefully I'll not spend more than 10 minutes on each of these topics. And so, by the way, feel free to interrupt and ask me questions anytime. Do you have anything now? Okay, so moving on. I'm going to set the stage because of the fact that I used boosting on many of these problems. So I just want to set the stage with this idea of boosting. The idea with gradient boosting is kind of very simple. Again, it was introduced by Jerome Friedman in 2001, and Professor Dietrich and others have extended this for learning multiple models, and then we have extended it to learn with relational databases. So the idea is that you start with some initial model, you make predictions on the data, compute the difference between data and predictions. Those become your gradients. So instead of fitting your at the next step, instead of fitting your model to the data, you will fit to the gradients, and so and then you will induce a new model. Now add that to the data, compute new predictions, and then the new gradients, and so on until convergence. Okay, so this is probably the simplest explanation I can give for functional gradient boosting. And the idea there is, if I don't have the math slide here, the idea is very simple. If I take a log likelihood function, typically you differentiate it with respect to the parameters. Now you can have maybe like a sigmoid function or something to get the probability out, and then you differentiate it with respect to the function. So the functional gradients come out to most of the times in a nice expression. Typically in a classification setting, it is the true value minus the probability of being true. Okay, and so that becomes your gradient. But in regression, it becomes the observed value minus the current predicted value. So it takes a nice form in most of these cases. These functions don't have to be trees, they can be any functions. Sometimes even logistic functions work beautifully for these problems. Again, I'm sweeping the rest under the rug. You can come and ask me if you have any questions, happy to help. Okay. So what we did was, we first learned this for multiple distributions. Because we were working with count data. For instance, the number of times somebody was admitted to a hospital, number of procedures, cardiovascular procedures that have to be done on someone. So we did that on Poisson data. We did this, of course, for multinomial data. For exponential data, we even had a very nice proof showing that it could converge to the global optimum only for exponential distributions, because we are predicting that when a heart attack would occur, not if a heart attack would occur. And basically, the longer you wait for that cohort, the higher was the chance of heart attack. Okay, so an exponential distribution fit very well. So we did all this, and then we learned multiple types of models. Again, I'm going to skip the details because I have not introduced statistical relational learning and AI, but we have done this for multiple models. These are the boring part. But the cool part was, we did this on multiple data sets, as I said, on cardiovascular study, electronic health records, Alzheimer's prediction. This was actually one of my proud papers. I just chose the wrong venue to publish it, because we actually did look at the three-way problem of predicting, just looking at an image back before deep learning. This is pre-deep learning. We are looking at an image to predict who's having Alzheimer's, who's cognitively normal. But the most important thing was who is in the middle, called mildly cognitively impaired. So if you just look at Alzheimer's or normal, even 12, 13 years back, if your performance, if the classification performance was under 90% in a perfectly balanced data, you should not even look at it, because predicting whether somebody has Alzheimer's or is completely normal is very easy. Throw in the MCI, then that's where it becomes difficult. For instance, during floods, if we had taken the images of some of your brain, we could be in mildly cognitively impaired. A death in the family, we'll be in MCI. The doctor that I worked with, Dr. Joe Mulgin, told me directly, Sriraam, if you get your NSF proposal rejected, and they take your, because then it was all that, right, for me. So it was, if I take your thing, given how depressed you get, you will be in MCI. The point I'm trying to make is, not all MCI people will go on to have Alzheimer's. So it was crucially important to identify which of the people that have MCI will go on to have Alzheimer's. And we actually got some very good results. This is 12 years back on this, and now of course everything is deep learning. So and then we also did some recommendation system, and I'll come to why this is important a little later. So again, in that data set that I talked about, remember the cardiovascular data set I talked about, we were looking at what is called as coronary artery calcification, which is essentially a calcium deposit on the left coronary artery. Okay, so this was back then in 2010 not very well known in the general US community. People did not hear of this coronary artery calcification. Then there is this CNN personality, an Indian doctor, I forget his name. He came and spoke about CAC, and then suddenly everybody that you talk to knows what CAC was, right? So this was just before that, and this is one of the key reasons for heart attack, right? If this grows, this becomes blocked, and then a person could have heart attack. So we were trying to predict by looking at data from 1985 to predict in 2010 who will have a heart attack, and turns out that of course our model had the better performance among all, otherwise I'm not presenting, boring. But what I want to show is the model actually learned. In the end we were able to combine them to a single tree, and I'll just go over the tree. Don't try to read this too much, it's in predicate logic format. So this is saying if this person A is a male and was between 35 and 45 in the year 7. So they were between 48 and 58 in year 20, which is where we were measuring, okay. So they were pretty much slightly on the older side, and then the cholesterol was pretty high in their 30s, late 30s to early 40s, 200 to 400, and if they smoke, they had a 97% chance of a CAC, as against a women who did not smoke in year 5, which is basically 1985, 1990, they didn't smoke, and this is the 5% chance of having coronary artery calcification. So it's very well known that men are more prone to heart attack than women. Actually, the first indicator of whether somebody is going to have heart attack in their 50s is with the gender, okay. But it is also true that men can handle, men can survive multiple heart attacks compared to women. So it's a very weird balancing thing that I still haven't figured out. The thing is, we also looked at, okay, what happens when we look at only year 0, only year, and then I add year 5 on top of it, and then I add year 7 information on top of it, 10, 15 and 20, there was not a lot of change. And we now, by the way, this is moved up to 0.9, closer to 0.9, this is a slightly older slide. But we have, basically what we are observing is, after 1992, we didn't see much change in predictive ability. And this could be because once a slob is always a slob kind of a thing, or people just don't change their habits, or they were just the way they are. I don't know what the deal is, but we are still investigating this as part of our current grant. We also threw all because Dr. Jeff Carr firmly believes that many of the cardiovascular events are not clinical. Well, there is a genetic predisposition, but other than that, it is social and economic that really causes this. And so, for instance, I'm going to again read this for you. This person is currently in school, which means this person is, the set of people who fell through this were actually in their 40s. They were in school. They were just two choices. They had a job or they were in school. So this is really, they were jobless. They were smoking cigarettes regularly. They did not pay for the residence. And in most of the cases, particularly in the population that we looked at, this means living with parents. So they were living with parents, but they had children. So it's a jobless adult male, typically males, who smoked regularly and did not pay for their residence and had children. So you can imagine the stress level. They have a 9 times chance of somebody who has a job, doesn't smoke cigars. I always say, I don't know if they are happily married, but they are married for 10 years. So they are in a stable relationship. Okay. So turns out that, yeah, just being married had a 9 times lower chance of this. So, they are in a stable 10-year marriage, and they don't smoke cigars, and they have a job. So these kind of things was very interesting for us, because we were able to learn this from this study. We can throw all the clinical data out, right? We can just look at physical activities, and I'll show you some results with physical activity as well. Physical activity, socioeconomic data, and see if we can mitigate these effects as much as possible. So we started figuring out if we can learn dynamic model, how things change. So we were learning at how coronary artery calcification changed as a function of exercise, number of children, marital status, occupation and stuff. And we were building these dynamic models that we could provide to the doctor to figure out where to intervene, right? I don't think it's correct ethically for the doctor to say, go get married. But the doctor could say, you need to lower your stress. And who knows how that could work out, right? We are also looking at older adults. This is as part of another group that we worked with. Actually I worked with a company which was building these Fitbit type things, and we were essentially getting the speedometer data, the gyroscope data, and one more. So there were like 3 or 4 sensors that we had, and we were trying to figure out what type of exercises they are doing and how it changed their heart rate and stuff. This work is still under publication. We're still under analysis. We have not finished the analysis because we wanted to understand which type of exercise for older adults improved their cardiovascular health. So this is a problem that we are currently working on, and of course we tried with LSTM, and we have some good results on predicting the type of exercise, but we are still not established the association between the exercise and cardiovascular results. Okay, so the thing is, again, thanks to Dr. Dietrich and Dr. Tadepalli, whom I worked with, we have pushed every single paper that we have published on our GitHub. So everything is downloadable, and we actually have an active tutorial that we are maintaining. We have users across South America, Europe, and India, of course, along with US, and we are supporting as when these bugs and other things arise, we are supporting them. So please take a look at it, and if you need any help, we are happy to help you. So I'm going to pause here to see if there are any questions about the cardiovascular part. Yeah. The first one was clinical data, socio-economic. Yes, the cardia data is actually the one that has come. We have socio-economic data there. We have physical activity data there. So they have these questionnaires. They have these sensors that they put in. Now the people who are survived, I think we have 3,600 people as of 2015. As of 2020, the data shows 3,400 and something. So we have still about 72 to 76% retention rate here, and we are looking at 66% retention rate here, and we are trying to see if they can be provided with all these Fitbits and stuff. So we have some physical activity there, but the physical activity in that data set is primarily in the form of questionnaire, which is why I'm working with another group where we are looking at, we are giving this out to people in Minnesota. This is with Mayo Clinic in Minnesota. We have a bunch of people who are provided with these things, and what are they called? CareBand. The name of that company is CareBand. So we've given them these things to figure out if their physical activity has any effect on the cardiovascular health.
So I was just wondering, because we have these 3 different categories of data.
Right.
Which is the more
So I think clinical data, right? I mean, clinical data is the one that's complete because you have images, you have lab tests. If I have to pick one, yeah, no, that's what I'm saying. If from the data, if I have to pick one, I would definitely pick exercise and behavior as the key. I mean, cholesterol level is an important thing, and how does cholesterol level increase? Not just like that, right? I mean, I used to eat 5 donuts a day, and clearly, there is a reason why things increase. So, yeah, if I have to just pick one, but I think it's a combination. In the end, it's a combination.
So my point was, if you can give weightage to these.
Right. So for heart attacks, I think behavioral things can definitely reduce the chances of cardiovascular events. But when properly supplemented with medical treatment, you can push it as far as possible. So I don't think I can pick one. I don't think my collaborators would like if I just picked one. So I would simply say that it's a combination, but definitely the behavioral data is important. I mean, there is some value to modifying our behavior. I think that's all I can commit at this point. But the thing is, we are able to predict, which means hopefully we can design interventions. That's the next step. Yes.
While you are describing how, you give an example about how a child asking questions his parent or something. How can it ask questions about a topic it doesn't know?
Good question. Yeah. Like LLMs, you should start hallucinating them. I hope you were in Dr. Dietrich's talk the other day. But I mean, the thing is, yeah, if you don't know, it has to calculate some sort of an uncertainty measure over things that you are reasoning about. And then it has to figure out that maybe the uncertainty is so uniform that I can't commit to anything. So here in our models, because of the fact that we build these boosted models, in the end we get a log likelihood of some sort out, right? Some likelihood out. and we use that likelihood to explicitly calculate the uncertainty, and then say here is the region. I'll give you an example hopefully where we have these questions that you can ask. So for instance, I think in their work we did this thing that says there is a direct, let me give you an example, right. So we came up with something that said as the degree of the person increases, the probability of gestational diabetes increases. So which means women with PhD have a higher chance of having gestational diabetes than women with whose bachelors, or in that case, women who skipped school, skipped college. And the doctor started laughing. Why? Because the conclusion is completely wrong. Because what we were supposed to learn was as age increases, the risk of gestational diabetes increase. The women population that we looked at, particularly the cohort in Indiana, the older women were always professors. The younger women were always college students, because it's a college town that we were looking at. The data was in and around Bloomington. So it popped out, right, and there is an uncertainty there, right. So we were looking at this and we were asking the doctor, this makes no sense, and he started laughing because it makes perfect sense for him, because for him every older woman that he has seen from Bloomington is actually a professor. So it was that kind of thing. So my point is that it's an active research topic and many people are working on it, knowing what it knows and what it does not know. And the idea again is not new. There is a paper from Leslie Kebling in I think early 2000s on knowing what it knows for reinforcement learning, and I think that's an important direction in general. Okay, yeah.
So you talked about the data itself and the correlations with all these different factors, but having this data and now you're developing a model to predict something from the modeling side, since these are all causal events,
Yeah,
so
yeah,
you say
yeah,
there's some
yeah, sure.
chain type of thing that
Yes.
model this thing.
We have used Markov chains, but not, we have used directed models called dynamic Bayesian networks, which are special cases of this, and we have done some work on that in this direction. We are now looking at causal models as well in temporal stuff, but again, right, learning them from data is not easy. So you have to start with an initial model and make local changes, and that's what we are doing at this point. I'll actually, in this one you will see when I'm presenting these. So one thing that I do want to do is go to the next step of the ladder and talk about what kind of domain knowledge can we add to the data, right. So one of the things that most of the times you get are what are called qualitative influences. As A increases, B increases. As age increases, risk of gestational diabetes increases, or as blood sugar level increases, risk of heart attack increases. And then you have something called synergies, where you can say something like higher blood sugar or A1C, a higher A1C with a higher HDL has a lower chance of heart attack than a higher A1C with a lower HDL. So now you are talking about good cholesterol, and you are saying that low good cholesterol and a high blood sugar level means you have a higher risk of heart attack than somebody with a same level of blood sugar level but lower cholesterol. So the point is that you can have this kind of knowledge very easily coming in, and you want to be able to incorporate this knowledge into the learning system. Turns out that because of the fact that in medical research they look at associations for a long time, these kinds of knowledge is in abundance, and if you ignore the knowledge and then start learning the data just from the data, we are missing many things. So we are our goal is trying to put this in. Precision versus recall trade-off, this happens all the time, right. I mean, you don't want when you have something like an Ebola, you don't want a false negative because that could cause a lot of problems. On the other hand, recommendation systems, I was telling this in COMAT and I had the email yesterday morning. LinkedIn sends me an email saying Indiana University is looking for a postdoc in precision health initiative. Okay, so first thing is I've been there, I've done that. Postdoc was 13 years back. The funniest thing about the whole thing was I am the PI of the precision health initiative grant, and it was my ad that went out for a postdoc when I was in Indiana 7 years back. That LinkedIn still wants me to apply. Okay, somewhere somebody did not pull down the ad, but the point is that they should be optimizing, they should not be optimizing recall, they should be optimizing precision, and they kind of leave that. So turns out that this is an important problem in many of these class imbalance data sets. Turns out most people are not married to each other, most people don't even like each other, so there are many things, right, that is fully class imbalance, and you want to be able to bring this into your objective function when you are learning the model. Okay, preferences, and this is extremely important again when you are talking of treatment planning, because Dr. A could be much more aggressive, Dr. B could say and this happens a lot to me because I work with two doctors on my diabetes. One of them is an older gentleman who's like, no, don't worry about the numbers, do this, it will come under control, and the other one is a younger doctor who's always after these numbers and trying to get that down. So they have these different methodologies, and funnily I trust both of them. I think both of them are successful, and I trust both of them, but the point is that each of them have a preference. Can we bring this in? The last one that I think is an important one that we have been working with is this idea of privileged information that was due to Wapnick back in 2012, I think was the paper on support vector machines, where you have some information during training that you don't have during deployment, and we actually have this in our actually new moms to be, right. So there is a cohort called Who's Your Mom, where we have the women put on smart homes. So they have a bunch of things inside the smart homes that they can query, we collect data on them, and then with the smart devices and stuff. But then when we are deploying it in the clinic, we are not going to give everybody who gets pregnant feedback, right. So the question is, how can we use the data that is there in the clinical study effectively to design some treatment plans where these data is not going to be available during deployment. So you want to use these things that are available only during training as some sort of constraints for your learning model that uses only the fully observable data. Okay. So what we have done is, again, we have a IIII paper on showing how to do this in boosting. I'm going to skip the details, but again, if you want to, I'm happy to talk to you about it in detail. But the idea is that in the end, it will boil down to an explicit trade-off between what I observe in the data and what I observe through the constraints. So how much does the data satisfy the constraint or violate the constraint, and how is the likelihood according to the data, right. So, and turns out that once we have this thing, and we showed that for many values of lambda, as long as it's reasonable, that is, you don't trust only the data and you don't trust only the constraint. So if you are anywhere between like 0.3 to 0.7 lambda, it's reasonable, we could get reasonable results. So it can work with when data is noisy but advice is very good, when the knowledge is noisy but data is very good, it can work. When both are very bad, well, there's no free lunch, so it's not going to work, right. So when both are bad, we can't do anything, but otherwise it's reasonable. Okay, and again, we have done this in the context of multiple problems. I'm going to skip that, and I'm going to talk about this new moms to be study, where, as I said, we have 10,000 women from 8 centers around the US. The one we were looking at primarily was in and around Indiana. 4% of the women had gestational diabetes. So we had many things like age, race, body mass indexed, polycystic ovary syndrome, family history, tobacco, physical activity, and a prior risk of gestational diabetes. We are, the first part of the grant, we are focusing on reducing the chances of gestational diabetes, because many women who have gestational diabetes can go on to have lifelong diabetes. For some women, particularly from China, they have a highest rate of gestational diabetes, but as soon as the kid is born, it's gone. But for instance, from India, if you have a gestational diabetes, there is a chance, there is a pretty high chance of that leading to a type 2 diabetes, and we want to see if we can somehow prevent that and mitigate it, right. So that's what we are trying to do. Again, we've learned multiple types of model. One thing that I think Saurabh just published in the biocomputing symposium is we had these several risk factors that we looked at, and we had monotonicity constraints. So as PRS score increases, the risk of GDM increases. As blood pressure increases, the risk of GDM increases. Age increases, and so on. And as physical activity decreases, risk of gestational diabetes increases. And then we combined all of them using this function called noisy-R. Again, I'll if you are interested, I'll talk to you more about this. But essentially, we learn a probabilistic graphical model on this, and we kind of got very reasonable results, probably the best that we could get. But the cool thing is, we were on par with the discriminative classifier, which was, but we were much more explainable and useful. So, and then we learned what is called as a probabilistic circuit on this, and again, we got very good results on the queries. Again, if you are interested in probabilistic circuits, you could talk to Saurabh, or it could talk to me. This is your UAI paper, right? Yes, this is from UAI this year. But the cool thing is, we learned a more consistent model when we are doing this, right? So this was learned only from the data. This is learned from our model. So if you look at this, the thing that we did with the data, it's always picking BMI as the first important predictor, while the prior risk goes down. But all we did was we said as prior risk increases, the risk of gestational diabetes increases, we learn a more concise model that is easier to understand and easier to explain. So the point I am trying to make is that if you use knowledge, if you have knowledge, please use that in your learning method. Do not ignore knowledge. Oh God, sorry, the contrast is terrible in this projector. So I'm going to read, and you got to trust me. So the first one is what the doctor told us. Okay, this is what we learn using our method, and this is learning from the data. So what we were trying to do was we were basically looking at this matrix of all the features with GDM, and then we were trying to see if we can do the inverse. Can we extract knowledge that we can present it to the doctors? And turns out that we extracted a few knowledge that the doctors did not have, while we were able to get. Let me read this one, which is let's see, quick to, yeah. So for instance, is there relationship between this one is saying, is there relationship between education and smoking, right? So as the as the education level, what is the difference relation between education level, smoking, and gestational diabetes? Turns out that the doctor said, well, there's probably nothing. But in the data, when we did it, we were able to see that most of the women who were educated did not smoke. So there was directly an inverse relationship that we were able to tease out of the model. Okay, and again I'm skipping this, and just want to say that we have ways to exploit understand these. In the new moms to be, we were able to extract rules that explained a deep probabilistic model, and we were this has appeared in probabilistic graphical model last year, and we were able to extract rules, about 31 rules that explained the deep probabilistic model over multiple risk factors, and we got some good results there. Okay, and again we were basically saying BMI is independent of age, education, and race in the cohort without GDM. So we were looking at how we can design interventions. So these kinds of explanations was would allow somebody to say, if you're smoking, maybe you shouldn't smoke. And we can't change the age, we can't change the race, but we can change the BMI, and maybe that's what we can go after. So these are the things that we can look at. But again, there is a very weird thing when it comes to BMI. We cannot just tell women go exercise, okay? Because women who have not exercised before, if they suddenly ramp up their exercise during pregnancy, preterm birth is one of the top results. So it's a very delicate intervention that we have to work with. So we can't just say go reduce your BMI drastically, right? So that's not going to work. So we have to figure out how to do this. Okay, and there's a really nice paper that I'm kind of proud of that we wrote in JAMA Network Open this year, where we were looking at the understanding the risk of prior risk and exercise. And essentially, if you have a higher prior risk, the best way to avoid any adverse pregnancy outcome is to start exercising before pregnancy. So understanding the prior risk is extremely important for preterm birth. So for instance, if the woman has the first kid is, let's say, preterm, to avoid second time preterm, you might want to start exercising before you get pregnant. So these are the kinds of things that we can design based on the rules that we learn. Okay, I'm skipping this. We are about time. We started 5 minutes late, I think, but I want to finish off quickly. So I'm going to talk about electronic health records. Again, we were looking at, this is a paper that's recently got some interest. We were looking at pediatric children population who are admitted into the ICUs, and many of them have a heart attack very quickly. And it turns out that with a reasonable prediction, about at least 0.86, 0.87 AUC-ROC, and this is a perfectly balanced data that we created, you can get a good predictor of heart attack about 5 hours before the heart attack. Before 5 hours, at least we can identify some of the kids who can have a heart attack. Maybe not perfectly, but at least we can find these signals that we can get and make sure that this chance of heart attack can be reduced. I was explaining to Dr. Dietrich, this also happened to another problem that we were in, which is the pediatric population. They put the kid on what is called as ECMO, which is this kind of like a life support machine, extracorporeal membrane oxygenation. Thank you. So, sorry? Yeah, ECMO. And the number of people who put, the number of people who can even handle the ECMO is actually on a much lower side. In the state of Texas, there are like 20 to 30 people at most who can do this correctly. And so when you put this person on, when they put the kid on the ECMO, the fact that the process of just putting the kid on the ECMO could cause an injury to the brain, and the kid could die. So we have to be very careful in doing this. We need to have a neurologist and so on. And we can just provide signals. Look for these features. If these features are very high, the risk of neurological injury is very high, and the person can be potentially saved because you need a neurologist there. This is a personal story that just happened about a year back. I can explain to you if you are interested later. But the point is, we can do things like this. Again, we can learn trees that talks about, putting the kid on this, where mean arterial pressure is like this. If the measured blood volume is this, then this is the chance, and you can come down and you can go all the way and have many signals. All these are ICU measurements. So this was actually from the electronic health record inside an ICU that we are looking at. It's a pediatric ICU, PICU unit at UT Southwestern, where we are looking at this data. Again, I'm going to skip, but essentially we can turn everything into a rule and actually figure out if in which category would this person fall, and then answer these questions. Okay, so and we also looked at multiple cardiovascular procedures, understanding who needs what. This thing. So, for instance, if somebody needs an EKG, what is the chances of them going into an angioplasty, and whom do you need to put in angioplasty, and who needs a valve replacement, and so on. So, we are able to learn these probabilistic graphical models from electronic health record data on figuring out which of these multiple procedures. We are looking at these three procedures: valve replacement, angioplasty, and EKG. This is from electronic health record at Regenstrief, and we are trying to figure out what are the medicines to be given to avoid going into, say, valve replacement. Can we even prevent this before that? And again, got some good results. So, I want to conclude exactly on time by saying that there is really, hopefully I have convinced you that there is no one ring to rule them all. So, no one method that is going to work very well for everything. It is okay if the model is not deep, as long as the reasoning is not shallow. So, as long as you can explain to the doctors what you are learning, I think it's much more useful. And I am not in an adversarial setting. So, for me, particularly the doctors that I work with, they all really want the AI systems to do well. They are not interested in asking, will this AI system replace me? Instead, they want to work with the AI system. They really want to use these systems so that it's potential. But the thing that I have figured out is communication is crucial. So, we cannot just go to a doctor and start, oh, I want to work with you because I'm an AI expert, right? You want to understand their procedures a little bit, so that we can talk the same language. And I say this all the time. I work with a high performance computing person, and we were trying to figure out how to scale a particular thing, and he said, I need an algorithm. And I said, oh, belief propagation. And he goes, no, that's an application. I want an algorithm. That's when I realized, as a computer scientist, what I call as an application, like from a machine learning AI side, is different from what a high performance person calls as an application. For him, the application is actually the algorithm that we develop, whereas his scheduling algorithms are more the algorithms that he was thinking of. So, the point I am trying to make is, inside computer science, we have different vocabulary. So, when you are going to talk to these experts, you have to understand sensitivity, specificity, precision, recalls, and so on and so forth, and talk to them accordingly, right. So, we have a long way to go, and I think I am more interested in medicine, but there is a lot out there. We actually have a DARPA funded grant that I called as Data Science Genome, where we are looking at ICML papers for the last 40 years. Hopefully, the package will come out sometime this year. And so, when a new person comes in and say, one of you comes in and you say, I want to do knowledge injection in neural networks, show me the papers, right. We should not start from 2017, because the first papers in that came from 1990. And can we pull these papers, show all the papers that came through, maybe present a knowledge graph that you can work with, and then say, okay, I can start here, read these papers in this order, and go on, right. So, I am just doing that for machine learning just based on ICML and NeurIPS papers. Hopefully, we'll come have that out. But we are also interested in learning from multiple experts. And because, as I said, multiple experts can have multiple views, particularly in medicine, and we want to learn from them, and adapting to include safety, ethical constraints. Not all constraints are easy, right. Like, for instance, who's your mom to be? Our first question is it okay to put them in a smart home? Are we okay to collect all the data from over them, right? And we have not really discussed this in greater detail that I really wanted to discuss, but that's how it is. And of course, finally, hopefully teach the human. So with that, I am done. I'm ready to take more questions. Yeah. So that's a good question. So how does the incorporation of constraints affect feature selection, right? So in some sense, the features that we work with are actually worked a priori before the knowledge. We decide and with the doctors on what are the most important things that we want to consider, because again, we cannot intervene on everything. Like age is a classic example. So but there are some predictive features. So what we do is we first do the feature selections, and then the constraints are obtained on the features themselves. So it's the order in which we do things. We first select the set of features, and then get the constraints and put them into the learning model. So it doesn't quite affect the feature selection, but yes, the feature weighting, the feature importances change based on the constraints, for sure. Right. Yeah, that could be one way to do it. I mean, you can basically say that I don't know what features are going to be present, and then you could learn multiple models by treating some subsets of features as privileged and not. But the ones that we do in medicine, we kind of know what we can measure. There are things that we cannot measure, there are things that we can measure, particularly when the imaging is the one that we are looking at in privileged information. So I know that when somebody walks into a neurologist, for Alzheimer's, dementia, we know we can get their cognitive scores, we know that we can get their electronic health record, we know we can get their images, but we can't really get their smart Fitbit data, whatever data that we look at. So we know that that's the privileged information that we want to deploy. For most of the applications that we work with, I think we know what is privileged and what is not. But again, with all these infrastructure, maybe you can search for that as well, search through that space. Yeah. Thank you. Yeah.
So regarding, it showed us that many diseases can be predicted using the social and cultural
Yes.
information that we have. So does this cultural and social really region is independent?
Yes.
Particular region.
Yeah.
So if it is true, if it is region driven, can these information be simply be copied to other regions, say other countries and say India?
Yeah, that's a good question. I mean, they cannot be simply copied, but we think they have to be adapted and generalized. So that's what we are doing right now. I mean, Saurabh is here for doing that. We have the data from Indiana University and the town around it, Bloomington. We also have data from India on the Garbini project. Now we are trying to figure out, can we build a model on this data A, build a model on data B, find out what is common across them, what is unique for each of them, understand how this can be, one model can be used in another. So we are still working on that for this particular data set. But for heart attack data, the priors change. So the prior risk of a South Asian, particularly South Indian, having diabetes is much higher than the rest of the world, including North Indians. Okay, South Indians are more prone to, South Indians and Brazilians are more prone to type 2 diabetes than most of the other world, right? And so the prior changes. So in some sense, the qualitative information that you have can change, but maybe the relations and the associations are still the same, particularly in the context of cardiovascular health. But in pregnancy, we are seeing already a lot of differences between the two models. It also depends on what is being measured in the two cases. So we have had people building, so if I go back to my cardia data, I had listed a bunch of things. There is cardia, there is Jackson heart study. And if we have compared the models against both, they are pretty much almost the same, even though they have completely different population. Cardia is primarily white. Jackson heart study is, there's a lot of Latino, African American, South Asian, along with the white population in the US. So the Caucasian population is still there. So it's much more evenly distributed because it's based out of Boston and a few other centers. So we've had some changes, but not a lot. So there are domains where I think there will be a lot of changes, and we have to figure out how to adapt them. Yeah. data. Yeah. Yes. Yeah. Right. That's perfectly true. Yeah. Right. I don't know. I mean, in the college town it was. Let me give you another example. It's so true, right? I'll give you another example. So in the US, people who live by the highways near the exits actually have a higher chance of heart attack in the highways than people who live a little bit farther from the highway. If I ask why, I think 90% of us will say noise, right? But the real reason apparently seems to be the access to good quality restaurants. So people who really live near the highway mainly tend to eat in the fast food area. So that is where, like you just said, we don't explicitly measure this variable, so we cannot quite explain it correctly. I agree with you, and I mean that's where we have to work with the experts to understand why a model particularly works or why it doesn't. So I'm with you. I agree. It's not easy, but that's a continuous problem, I think. Yeah.
Considering race of a person makes us a racist.
Hopefully not.
If not, then the entire thing.
See, look, considering the sex of a person doesn't make me sexist. It's just a predictor that comes in. So yes, I mean, look again, right? It's we can laugh it off, but you have a fair point. So for instance, if I'm going to build a insurance model, and then the insurance company says, if this person is 21, don't give them, or a credit card company says, don't give them a credit card. I mean, really, you want to invest in the 21-year-old to give them a credit card, help them grow up, rather than give it to a 45-year-old like me, saying, yeah, here, have one more credit card to your 7 credit cards that you already have, right? And that's how it should be done. So yes, the fairness questions are there in every problem, and we have to understand them deeply before we deploy them. That would be my answer. But just because you use race doesn't make us racist, but potentially it can. If you use the race as a discriminator for a particular treatment, then yes. But you could positively do this too, because when I go to the doctor, the first thing the doctor says is, oh, you're South Asian, I need to really take care of you. Right, and that's a positive spin on the whole thing, right? Because they're looking at me, they say I have diabetes I had diabetes in my 30s. They're not surprised. I am. My parents are shocked. I am surprised, but my family is full of diabetics, and so there is a very high risk for me, and that doesn't make that in this case her racist. But I see the point. I think yeah, we have to understand this. If it is relevant, I don't know. I mean, it depends on the problem. Truly depends on the problem. But there are cases. I mean, do you have a different answer, Professor? I don't know. I mean, it depends on the problem, I think. Right. Yeah. Yeah, that's a good question. Admission due to caste, is that racist? I don't know. Casteist? I don't know. It's tough. I think the social side of things are different. And again, what is normal in one place is not normal in another. What is considered okay in one place is not considered okay in another. And so we have to first understand the social aspects of things are much more difficult, which is why I tend to try not to do that explicitly, but yeah, I see, yeah.
You spoke about the three classes of data regarding the scenario and
Yeah.
research. So, what if there is like an outlier coming in? Like say that a person suffers
Yeah.
heart attack, let's say through alcoholism.
Yeah.
So, do you consider that just to be an outlier and then handle it through uncertainty, or like do you
Yeah.
start collecting those data as well for everything?
That's a brilliant question. Yeah, I mean, you can have outliers, you can have new observations, new features that come in. I mean, maybe alcoholism was not measured 20 years back, and now they are measuring alcohol content, particularly for liver. I mean, there's a lot of liver articles that I am reading, how even consuming moderate amount of alcohol actually increases the risk of liver cancer, right? There's enough proof now to show that. And what happens if these things, so that's why these models need to be refined, continuously refined, whether it's with data points or whether it's with knowledge, they have to be refined. and that's what I think. They have to be refined. I don't know if I'll call that an outlier as much as a new observation, particularly in the context. But there could be outliers. There could be people. I know somebody who doesn't wear a mask, who tests regularly though, but has never got COVID, right? And they was telling them that there is an NYU study on the super immune people. Maybe you should go enroll. Is he an outlier? I don't know. But he tests continuously. I think, I don't know what he was trying to do. He never wears a mask, but he tests, he could be an outlier, and we have to understand that. So yeah, but we need refinement. That much is clear. We need refinement. You can't just say, I built this model 10 years back and it should work now. So both. It has to be both. Data could be new data, new features, new lab tests, new populations that we have not uncovered. It could also be new knowledge that we got over time that we have to include. Okay. Thank you. Thank you.